In the previous topic, we have discussed about several types of interrupts, what is the meaning of interrupt, how it is classified. So, like hardware and software, maskable and non-maskable, vectored and non-vectored. In case of vectored interrupts, whenever interrupt is triggered, the program control goes to a specific address location in the memory. In other words, whenever interrupt is triggered, the relevant program control is automatically transferred to the location. In case of non-vectored interrupt, for example, say INTR, interrupt request, it can support 8 input-output devices for interrupt mechanism. And hence, with respect to INTR, there is no specific address location where the control can lead. And hence, INTR is called as non-vectored interrupt because it may reach to any of the 8 software interrupts vector locations. So now we shall discuss how actually this interrupt mechanism is established in a particular microprocessor. For reference or for understanding purpose, I would like to discuss with respect to 8085 trap pin. So if I ask you a question, what is the interrupt which has got highest priority in 8085? Trap. Similarly, many processors will have different kinds of interrupt mechanism, and the number of interrupts for hardware and software would be definitely different. Yes. Now, let us consider the interrupt mechanism, which is very important for understanding as per the practical orientation which is concerned. And there are several types of questions which can be possible in this interrupts. And here, this topic may look like out of syllabus, like interrupt comes under IO organization, but it is a part of control unit. So, it is very important to understand the importance of this interrupts. Yes. So, now let us discuss the importance of trap interrupt, how it is used and how the program control is shifted from a particular program to the interrupt service routine. So, by the way, what is ISR? I think in the previous topic we have discussed what is ISR. It is a program that is executed in response to an interrupt. In 8085, there are 8 bytes allocated for every ISR, vectored interrupt ISR in the memory. If the length of that ISR is more than 8 bytes, then we can use some programming logic like unconditional jump so that we can shift the program control. For example, say the 8 bytes of memory space is not sufficient for the interrupt service routine, and hence we can write the ISR somewhere else in the memory which is present, and the reference of this particular value means, for example, this address location can be written here. So, this is where we can provide the reference. So, within the 8 bytes, we will not write the total application program. When the interrupt is triggered, it will just execute a part of the program. If the length of this ISR means if the number of instructions in the service routine is more than the allocated one, we will just write a reference address, and hence the program control can be shifted to this particular address. So, in gate questions, such type of analysis type of questions can be most probably given. So, you should understand that in gate, the analysis type of question and the practical issues of questions are more expected. Therefore, you must be thorough with the basic concepts as well as the notation of the actual operation of the process of this interrupt. So, let us discuss how actually this interrupt mechanism can be considered. Fine. I am considering one application which is industrial oriented. For example, in an industry, the highest priority is meant for the security of an employee or the devices, whatever it is, but most probably the employee security. Therefore, there can be different types of alarm systems meant for fire accident or some other type of accidents. There are different types of sensors. Let us consider that there are some smoke sensors or fire sensors which can detect the smoke and all, and that can be implemented by some hardware logic. And whenever that fire occurs, our job is to immediately switch off the power supply for important blocks and raise the alerts, alarm or whatever it is, siren. Such kind of things can be done. So, now let me consider how the operation can be done. Let us consider that this is the processor, okay. Okay, fine. Now let us consider this as the processor, and in the memory there is some service routine for the trap interrupt. There is some service routine. Okay, so this is processor and this is memory part. So let us take the memory to be some 64 KB maximum value. Okay, so now I am considering like this is the bus between the processor and memory. Okay, fine. So yesterday we have discussed, or in the previous class we have discussed, what is the vector location for trap. So trap vector location is 0024. So in the memory at the location called as 0024, to certain locations the ISR of trap is present, means the application program what you want to do. So here this is the processor, okay, and there is some sensing mechanism here. Let us consider, like for example, say here there is the trap signal, and say that there is some sensor here, smoke sensor. There is some smoke sensor. Say there is some smoke sensor. Okay, and I am taking some comparator. Okay, comparator. So this is some smoke sensor or fire sensor, whatever you consider. And out of this smoke sensor or fire sensor, the signal is given to some kind of comparing circuit, because when there is no fire also, due to dust and all, some smoke may arise. So there will be some reference point for it. Let us take some comparator here. Okay, this is some comparator. Okay, there is some circuit. So the output of the smoke sensor is given to this comparator. It will be always compared by certain reference value. Okay, certain reference value. Okay, fine. And the output of this particular comparator is given to the trap. Fine. So trap is a vectored interrupt, and this is program counter. Okay, how it looks or how it goes, let us see now. And here there is the instruction register. Okay, instruction decoder, and there may be a couple of registers inside. Okay, fine. So here the ISR of trap, this is memory part, and I am considering the ISR of trap from 0024 to some 002B. Let us say the program is of 8 bytes, whatever it is, some program is present. Okay, so these are the lines, address lines, data lines, the path is considered, but never forget that the data path between memory and the microprocessor is bidirectional. There is a latch in between, so you should never forget that basic concept. Okay, now observe here, whenever some smoke occurs or fire occurs, it will be given to the trap signal. So there is a inbuilt mechanism, PC will be loaded and the corresponding program will run. But observe carefully, when the program runs, this program should initiate some hardware logic. So I am also considering some hardware logic here. Let us say there is some hardware logic. There is some hardware logic which is connected to the bus. So this is connected to the bus. Let us take this value as connected to the bus. So this value is connected to the bus, and say I am just writing here. Okay. So this is the bus. Okay, fine. So this is the hardware logic. Hardware logic. So whenever this hardware logic is activated, we will have some circuitry here which will provide some, like it will operate the power supply logic. We will provide some logic here, okay, such that this will trigger the logic here. So this is some cutoff circuit for power. Okay, there is some cutoff circuit for the power. And similarly, you may also have some siren, blowing of siren here. So there are certain things which are possible, right? So this is actually the interrupt application. Now let us see what are the sequence of events which may take place while an interrupt is received by the microprocessor. Okay, let us take number 1. First, when there is no smoke or no fire, nothing will happen. It will be just comparing the values. But whenever some smoke has occurred, let us take the sequence of events here. Number one, say the fire has occurred here. I am considering like this. So say number 1, the fire has occurred. So definitely the output of the sensor will be more than the reference value. So this will activate the interrupt. Number 2, and now tell me the signal has come under the trap pin. So what kind of triggering is trap? It is both edge and level triggering. Now we will come to know why actually trap should be both edge and level triggered also. So here when trap is received, the trap interrupt has got highest priority in 8085, and hence as it is a vectored interrupt, inside the microprocessor there is some built-in logic such that the program counter is automatically loaded by the vector address of the trap. That is the actual meaning of vectored interrupt. Vectored interrupt means whenever the interrupt is triggered, there is some built-in logic such that PC is loaded to the with the vector address, and hence the PC contains, what does PC contain? Address of the next instruction, and hence the program control will go to 0024. So what is there at 0024? Whatever the interrupt service routine that will be executing. So from here, you know the story. Opcode is brought from memory to the IR, decoded, it will go on running the program. So when this application program runs, this will go and activate the hardware logic, and this hardware logic will activate the power cutoff circuit, or it will blow simply some siren. So it is power cutoff circuit, and also it may have some siren or alarm such that the people may run from that particular location. So this is how actually the interrupt mechanism can be considered. Fine. So that's how the program will run with respect to one interrupt. So I have taken for trap. You can observe for any other interrupt also the story is same except for the INTR. So now observe here, you know one important thing, like what is vectored interrupt? Vectored interrupt means there is some built-in logic inside the processor such that when the interrupt is triggered or switched on, PC is automatically loaded with the vector address. That's called as vectored interrupt. Now, why the trap interrupt is both edge and level triggered? In the previous class, we have discussed that the trap is both edge and level triggered. It is both edge and level triggered. So now it's very easy that definitely interrupt should rise on the pin. That is common. But whenever the interrupt has raised, it will wait for some time. Okay, that is approximately 3 clock periods with respect to the trap interrupt. Why? Because let us say due to noise also the signal may rise on the trap pin. Then it will become a red signal. So the siren will blow. So people will understand today is holiday for the company. Some accident has occurred. That is wrong interrupt. To avoid such type of erroneous responses or sensing of interrupt, trap has been also provided with the level triggering. It means it will wait for 3 clocks unless until it is high, then only the interrupt service routine will be accepted. That is the reason for having both. Why not for other interrupts? Because they are having some less priority. They are maskable interrupts which can be switched off sometimes. So that is how we can understand the mechanism of interrupt here. Fine. Let me tell you one more important thing here, like whenever interrupt occurs, now observe carefully. Let us say let us consider that the processor is working with some program, it is solving some program, right? So program counter will contain address of next instruction, that is known to us. This trap is hardware interrupt or software interrupt as per our discussion. Can you recollect? It is hardware. What is hardware? In the 40 pins of 8085, one pin is the trap pin. Now observe carefully. For example, let us say processor is running some program, some execution of the program. Say it is running some instruction of some 00, say like 80056. Okay. Let us say it is executing some instruction at 8090 address. Okay. It is executing the instruction which is present at 8090. Assume that the next instruction is at 8091. 8091. Now observe carefully. Whenever it was running some instruction, some X instruction at 8080, 8090, at that time on the hardware pin it got the trap interrupt. It got the trap interrupt. So now observe carefully. Microprocessor is not a human being to think or remember the address where it has to go back. So therefore what happens is, before it goes to the ISR, let me tell you like this, before it goes to the interrupt service routine which is present at other place of memory. Now tell me, where is ISR of trap located? 0024. Therefore, if it is changing its sequence of program from one address to another address, how can it come back? It's not possible. That is why before it starts the application program, first it will load or it will push the value of program counter which is 8091 automatically into the stack memory. So whenever the interrupt occurs, what happens? First, the processor, number one, the microprocessor completes current instruction, then it will load the PC value or it will push the PC value into the stack memory. So then it will push the PC value into the stack memory. Number 3, then it executes the ISR, and generally one instruction called as return is used in as a last instruction of ISR. There is one instruction called as return. So in this particular instruction, it will come back, means it will take the PC value which was dumped into stack memory. I think you remember what's the purpose of stack. What's the purpose of stack? It is used to store the temporary data and also the value of program counter when subroutines are used. So what is subroutine here? The interrupt service routine or subroutine, both are same. So hence what happens, it will execute the ISR, then number 4, it will pick PC value, or you can say pop PC value from stack. Okay, then it will continue the program as it is. So it will pick the value of this from the stack, then it continues the routine, okay, from stack and continues and loads PC. Okay, so these are some important points when the interrupt occurs. You may have several type of objective questions. So when interrupt is received, interrupt occurs, first it will complete the current instruction, then PC value is pushed onto the stack, then it will execute the ISR, control is shifted to this ISR, then this is number 1, so interrupt has occurred, number 2, push the stack, number 3 goes to ISR, number 4 in the written instruction picks the PC value, and number 5 it continues the previous program which was already running. So these are some important sequence of events which would take place when the processor responds certain interrupt. So there are several type of questions which are possible by this sequence of interrupt. The same concept can also be understood for call instruction. There is one instruction called as call instruction that is same as interrupt, but it is one instruction, but these are interrupts present on the pin. So we shall discuss how actually the concept matches in the instruction set architecture or instructions, which will be discussed later. I hope that you understood the concept of trap very clearly. Right. Now let us go for the next. You can write one note. In case of vectored interrupts, there is a built-in logic within the processor such that the vector address of interrupt is automatically loaded into PC. If the length of ISR or application program of interrupt is more than the predefined bytes, an unconditional jump instruction can be used such that the program may be continued further. An unconditional jump instruction can be used such that the program may be continued further. So this is how one vectored interrupt, and that too highly prioritized interrupt, will work in the industries. I had one experience while taking the classes at some of the places in India. So two people got some interview in the real-time application like steel plant and all. So I was discussing the interrupt topic in my classroom, but these two people were just present at the beginning, but later they left. As they have interview, they went to the location, so on, etc. After the interview, they came to me, sir, whatever was discussed, so they don't know. They have been asked some location, like some questions in interview. In a steel plant, the temperature is too high. Okay, the metal should be melted and all. So manpower will not be in that chamber. Everything is sensor based. So they were asked questions about the interrupts. So how do you control these applications? So they would have talked about the interrupts and all, but these people couldn't answer as they couldn't go through this entire data. So later after the interview, they came to me and they saw the notes. So these were the same questions which were asked. So in industries, when you go for practical companies, whatever it is, they won't ask you the theoretical questions. They will try to ask you application questions, how the candidate is able to apply the subject. So they don't expect completely 100%. At least you must approach towards that direction. So I urge you people to try to understand the basic concepts very, very clearly. Right, that is mechanism about the trap interrupt. So that is about vectored interrupt also. Now we shall discuss about the non-vectored interrupt in 8085, which is called as INTR. So INTR stands for interrupt request. INTR stands for interrupt request. This is the only non-vectored interrupt in 8085. It has got least priority, but the advantage of this INTR is that it can support 8 IO devices, but one at a time. It means among the 5 hardware interrupts, 4 interrupts can be uniquely present with one device. By using INTR, you may connect 8 IO devices by using one extra interfacing component called as 8 to 3 priority encoder. Fine. It means altogether, you may handle some 8 plus 4, 12 interrupts with 8085. If you go with 8086 microprocessor, it can handle up to some 256 interrupts. So based on the design, based on the type of microprocessor, there are different possibilities. Okay, so it's not fixed for all. There are different types of interrupts which are possible. It's not same in all the cases. Fine. Now let us consider this INTR. There is one more pin which is with respect to INTR, that is INTA. You will come to know how it is used now. For example, let us consider the INTR. Before this INTR, you should know the software interrupts. Let us discuss that, and then I will draw the block diagram. Right. So there are 8 software interrupts which are generally called as RSTN. The value of n is from 0 to 7. The value of n is from 0 to 7. So these are also vectored interrupts. They have got 8 bytes each. So RST0 starts from 0000H to 0007. RST1 starts from 0008H to 000F. And RST2 2 is from 0010 to 0017. RST3 is from 0018 to 001F. RST4 is from 0020 to 0027. Similarly, RST5 is from 0028 to 002F. And the RST6 should be from 0030 to 0037. At last, the RST7 will be from 0038 to 003F. So these all are vector locations or vector addresses for the software interrupts. So very simple, it's a game of hexadecimal number. In the very first class I told you that the total subject just runs around the hexadecimal numbers, binary, so on, etc. Right. So these are all different types of software interrupts. Now, if you want to understand the mechanism of these software interrupts, you should know how actually the INTR is used. Now observe carefully. This INTR is a hardware pin, but it doesn't have its own location. It has to use any of the 8 software interrupts vector locations. For example, it is based on the programmer's choice. Let us say I am the programmer. I can use any of the software interrupts vector locations to store the ISR. For example, there is one IO device. For that IO device, there is some application program called as ISR. I want to use the RST5 vector locations in the memory to store the ISR. So I want to store the ISR of IO at these 8 locations. But understand carefully, RST0 to RST7, are these software interrupts or hardware interrupts? Software interrupts, means they are instructions. Every instruction, this RST5 is one instruction. So it's not a pin, this is one instruction. That is the first thing you should understand. It is one instruction. Every instruction will have a code. That code is called as what? Opcode. So tell me, in 8085, total how many instructions are there? 246. We have discussed in the last class. So the opcode length will be how many bits? 8 bits. It means that these 8 are instructions. They have some opcodes uniquely. This is our assumption that ISR of IO is priorly stored in the vector locations of RST5. Now, in order to use INTR, what is the mechanism? Let us discuss now. For example, say, okay, assume that the opcode of this RST5, let us say, opcode of RST5 is something like 90H. It's not the 90H, but let us assume that it is 90H. Fine. Now, let us consider the mechanism which is involved for the INTR. So, most probably the questions will be given with respect to trap and with respect to INTR. So, these two are quite different. Let us discuss what is the scenario. Fine. For example, say this is INTR, this is the processor and this is memory. Okay, let me take a little bit. This is memory. And there is some IO device, and to generate the opcode there is some hardware which is required, hardware logic. And what is the sequence? Let us discuss now. Fine. This is the processor, memory, and say you have stored the ISR. You have stored the ISR at some 0028 to 002F. So RST5 vector locations 0028. Okay, 0028 says 002F. So this is where the ISR of IO is present. Means application program. And by the way, you know that memory is connected with the processor, that is common logic. Okay, fine. This is address bus. And there is some hardware logic here. there is some hardware logic so this will provide opcode of RST5. So what was the opcode of RST5? We assumed some 90H, and this hardware logic is connected with the IO device. This is the IO device. Say this is the this is IO device, whatever it is, and there are some important pins to understand here. So one is the INTR and the other pin is INTA bar. So for the first time we are discussing about INTA bar. We have not seen this line till now. It is meant only for INTR, not for the vectored interrupts. That's the main thing to follow, right? So this is the sequence, how it follows. Let us discuss now. So you know that the INTR is connected with this and INT is also ready. How it happens, let us see. And don't forget that the hardware logic is also connected here, and the main interesting point is that the hardware logic is connected to the lower 8 bits of the address bus. It's not 16. So opcode is 8 bit only. Whenever the bus is striked off and written like 8 bit, you should understand that the bus length is 8 bits. Okay. And here is the PC program counter. This is program counter and IR, instruction register, decoder, so on, etc. Now let us consider this. So our assumption was we have stored the ISR of IO at vector locations of RST5, at vector locations of RST5, and opcode of RST5 is 90H. RST5 is 90H. Okay, right. So how it actually happens, let us see now. Okay, fine. So number one, this is a sequence. So assumption is we have stored at RST5 locations and we have designed some hardware logic to generate the opcode of RST5. Now what is the sequence? Let us discuss elaborately and clearly now. Okay, fine. Now in order to use INTR, the programmer should first select one of the 8 software interrupts to store the ISR of IO device, and one external hardware logic must be built to generate the opcode of corresponding software instruction. And other thing is that the microprocessor is something different, means its behavior is something different with respect to INTR. In case of vectored interrupts, whenever interrupt occurs, there is some mechanism inside the processor such that it can understand that some interrupt has occurred. But in case of INTR, which is least priority interrupt, the processor will itself acquire the INTR pin in the last clock period of every instruction. What is one clock period with respect to 8085? If operating frequency is 3 MHz, what is the clock period? 0.33 microseconds. So let us say that there is some instruction going on. Okay, there is some instruction. This instruction has got some clocks, T1, so on, etc., some T10. Let us say 10 clocks are required for the instruction. So in the last clock period of every instruction, the microprocessor will check this INTR pin, whether interrupt is present or not. So what happens is, in the last clock period, let us say it is executing some instruction. Even though INTR has come at some place, processor doesn't bother. It will check till 10th only, T10 only. Let us say the instruction requires 10 clocks for execution of a particular instruction. Only in the last clock, INTR pin will be verified by the microprocessor. So let us see what happens now. For example, number one, say I am just writing with respect to clock so that you can understand easily. So let us say this is first clock of the instruction. So instruction clock. Okay, this is first clock. So second clock, so on, etc. This is 10th clock. Okay, let us assume. Say that the INTR pin has raised in the first clock only. First clock only you got the INTR signal. But processor doesn't bother. Why? It will check only in the last clock period of every instruction, whether INTR is present or not. So the INTR should have its response, the interrupt should be present on the pin till the processor recognizes it. Yahan tak rehna chahiye. When the processor recognizes the interrupt in the last clock period, that is 10th clock, then only the actual interrupt will be responded. That is the main thing to follow. For example, if an instruction requires 16 clocks, in the 16th clock only processor will check INTR. If an instruction requires only 4 clocks, in the 4th clock only it will check INTR. So, checking of INTR is not fixed in the clock period. Based on the instruction, it may happen. Right. Now, whenever INTR is received by the microprocessor, it will verify the status of this INTR in some clock period based on the instruction. Say in the last clock only it will verify. If INTR is present, now tell me, INTR is vectored or non-vectored? Non-vectored. So when INTR is received, processor doesn't know where to go. There is no built-in logic. That is why it is responding to the interrupt by sending one INTA. INTA stands for interrupt acknowledgement. INTA stands for interrupt acknowledgement. Interrupt acknowledgement. So this interrupt acknowledgement is required only with respect to INTR, not for other interrupts. Fine. So when interrupt acknowledgement is received, this IO device will now activate the hardware logic. So what does hardware logic contain? The opcode of the instruction. It means now we are supplying the instruction from outside of the processor. You are not present, they are not supplying inside the processor. Opcode is coming from outside. So now observe carefully, number 1, number 2, it supplies the opcode, that is number 3. Now tell me, think logically now. 90 is one of the instruction of microprocessor among 246 instructions. So whenever 90 is decoded, number 4, whenever 90 is decoded, it is a vectored interrupt called as RST5. In case of vectored interrupt, what happens? There is a built-in logic inside the processor. Now understand, I am saying there is a built-in logic. Why? 90 is the opcode of a vectored interrupt RST5, and hence this PC will be loaded with 0028. Now tell me, what does PC contain? Address of the next instruction, and hence the program control will be automatically shifted to the vector location of RST5. Hence the program, whichever it is, the program will be running. This is how the program flow or sequence will be present. The sequence of events are possible with respect to INTR. Now for example, you have stored the ISR at RST5, so you have designed the opcode of RST5. If you have stored the ISR at some other software interrupt location, that particular opcode will be designed. If you want to support 8 different IOs, instead of the hardware logic, we can use one 8x3 priority encoder. That is the significance of INTR. So we can understand some questions which are possible with these interrupts. Now observe, hope that you have understood this. So tell me, why INTR is called as non-vectored? Because there is no specific address location for INTR. Whichever the software interrupts you select for storing the program, only at that particular location it can move. So there is no fixed location for INTR, and hence INTR is called as non-vectored interrupt. And one more important point is that this interrupt acknowledgement with respect to 8085 is required only with respect to INTR, not for the vectored interrupts. That is the concept of different kinds of interrupts which are possible in 8085. Okay. That's about the 5 pins and plus 1, that is INTA with respect to 8085. There are some instructions which execute with respect to interrupts in 8085, like set interrupt mask, read interrupt mask. So let me just tell you so that you can follow easily. Instructions related to interrupts in 8085. One is called as enable interrupt. Okay. So these are all meant for only maskable. You cannot enable or disable the trap. Next one is disable interrupts. Next one is SIM, stands for set interrupt mask. Set interrupt mask. And another instruction is RIM, called as read interrupt mask. So don't forget that all of these instructions are only for maskable interrupts. Maskable interrupts. It's not for trap. Trap is non-maskable with respect to 8085. That is how the operations can be done in the interrupts. Fine. This is about the interrupt mechanism in 8085. So never forget the flow which I told you. Like when interrupt is received, the processor will first store the next value, means PC value, into the stack memory. Hence, it will go to the ISR program, application program, run it, come back to the main program by picking up the PC value from stack, then it continues the main program. So that is how the sequence can be understood. Fine. Right. There are some signals called as status lines, so that you can understand easily. There are two more signals called as S1 and S2. These are status signals, status lines, which give the status of bus cycle. Means what is the status of bus cycle? What kind of operation processor is performing? Now observe carefully. For example, I am staying in one office. Let us say I am in my office. You might have found in the government offices, when the officer is inside, there will be two bulbs outside the room at the door. One is red, other one is some green, something like that. When the officer is busy, automatically red bulb will glow, indicating that sir is busy. He doesn't want to be disturbed. In the same way, processor delivers its status on few pins called as S1 and S0, along with one more pin IO/M bar, indicating whether memory or IO operation. There are some fixed status for this. So just for understanding, I am giving you, nothing to worry about it. Like for example, these two status lines S1 and S0 can be added with IO/M bar, and some status are prepared for this. Okay, status is fixed always. Status is fixed. For example, say 00 is a status indicating that processor has stopped. 01 indicates that processor is performing some write operation. 10 indicates processor is performing some read operation. But always understand, processor can do memory write or IO write, memory read or IO read also. How to find out that? By considering this one. So if this is 0, then it is memory write operation. So status is fixed. If it is 0, this is memory read operation. Now tell me, when the processor is has stopped the execution, is there any question of IO bar M bar? Because halt is neither memory nor IO operation. So we simply write Z. So Z means what? High impedance state. We have studied about tri-state. Do you remember? High impedance state. High impedance state means there is no current flow through the line. There is completely zero current. There is no current. Fine. Similarly, 0, 1, 1 is meant for opcode fetch. So whenever the processor is performing some opcode fetch operation, by looking at these three lines, the other devices can understand what is the current status of microprocessor. That is why status lines are present. Similarly, 101, can you try it? 1 means IO. 01 indicates write. So what is the status? IO write. So it is not fixed for a processor, it depends on process. 110, what's the status? IO read. And 111 is when the processor supplies interrupt acknowledgement. And there are two more status also. Let us consider. One is hold, other one is reset. I'm just writing here. This is reset. Okay, what's the meaning? You'll understand. So this hold and reset we'll come to know in the next discussion. Fine. That is how actually the status lines are present. So nothing to remember, you can easily understand that processor status can be understood on the by looking at these three lines by the IO device. Okay. Till now, we have discussed elaborately about the different kinds of interrupts which are possible in 8085. So this is actually the 8085 microprocessor which we are discussing till now. So it's amazing that in 70s itself, people were able to design one such a powerful processor which was able to solve most of the problems. Later on, they have gone for other type of high-end processors because 8085 was handling only less amount of memory because address lines are 16, maximum of 64 KB can be connected. So they have gone for 8086 where 20 address lines are possible and 2 port 20, that is 1 megabyte is possible. Fine. In all these pins, every pin is one signal. I hope you have studied about the address bus. Okay, sorry. You have studied about the address bus. You have studied about this address bus, lower byte of address bus, multiplex bus. You have also studied about the higher byte of address bus, and we have studied about different types of interrupts which are possible, and also the two pins where the crystal oscillator can be connected. Okay, crystal oscillator is used such that the frequency is more stable. Fine. And these two pins are meant for serial communication to receive the serial data and to transmit the serial data bit by bit. Similarly, coming to the other side, we have studied about these all signals, the status signals and the control signals, and you know about the IO/M bar, and processor 8085 operates with plus 5 volts DC supply, and this is, by the way, the ground signal. Okay, ground signal. In some processors, the grounds can be more than one also, so that the loading effect or impedance mismatch can be avoided. Fine. What are the left of pins which are present here? If you observe here, this ready signal is meant for communicating with the slow speed IO device. For example, let us say this is processor. Let me just show you how it can be done. See that, okay. For example, let's consider like this. If this is processor and there is some IO device and this is slow speed peripheral, right. So there are some pins which have to be discussed now. Whenever the processor communicates with a slow speed IO device, it will check the status of the IO device on the pin called as ready. So ready is one input signal to the microprocessor. If the device is sending a ready signal, then only the processor will either send the data to IO or receive the data from the IO device. So ready is one input so that it can check the status of the slow speed peripheral. So ready is required whenever it is communicating with slow speed. For example, ready is 1, then only the processor either transmits or receives data to or from IO device. Similarly, when ready is 0, the processor waits for the IO because processor is not communicating with high speed, it is slow speed. That is why when ready is 0, processor will wait unless the device is ready. That's the purpose of ready. Let us say you want to reset the microprocessor, then that is done by reset in. So when you provide a low signal here, the microprocessor is reset. So what happens for the reset? So for reset of processor, automatically the program counter value will be loaded with 000H. It means the program again starts from the address called as 000H. That's about the reset in. Let us say 8085 works with operating frequency of 3 MHz. The same frequency can be used to connect some IO device to have the same frequency, that is called as clock out. So the same frequency of the processor is available on the pin. Similarly, you can reset the IO device through the pin called as reset out. This can be connected to reset pin of the IO, and this is clock input of the IO. For example, you might have observed in calculators, after solving one problem, you want to go for the next problem. What we generally do? You press the AC button. So that AC is something like a reset signal. What is the IO device here in the calculator? Display is the output device. So when you press AC, when reset is given, it is connected to the display reset. So the display is again washed off. It is again from the beginning. That is what we call as reset. So these are the pins which are present in the processor 8085 pin diagram. Right. Let us go for the other pins which are left off. So you have studied about all of them. Now observe carefully, there are two more pins which are present here. So what are the two more pins here? Observe carefully, hold and hold acknowledgement. So ready is with respect to slow speed IO, or IO is also called as peripheral device. But sometimes IOs are always not slow. IO device can also be speed or fast. One such type of device, let us say, is let us say CD writing mechanism. Therefore, you should transfer huge amount of data to the CD drive or DVD drive. It will work very fast because writing should be very fast enough on the disk. Therefore, these two signals are meant for communicating with a high speed IO device, not slow speed. So here, these are not slow speed, these are high speed IO device. So this is for high speed IO device. So this is also, these are also important two signals which are meant for communicating with high speed IO devices. And one such operation is linked up with high speed data transfer, that is called as DMA, where DMA stands for direct memory access. Direct memory access operation. Direct memory access operation. Fine. We shall now discuss about this topic which is involving the pins called as hold and hold acknowledgement. Right. I am discussing about the two pins called as hold and hold acknowledgement. To understand the pins, you should know some basic data. Okay, right. Let us consider like this. Say this is processor, this processor, and there is some memory here, memory, and there are some devices. There is some bus, let us say there is a bus here. So this is bus, communication path, and memory is also connected to this particular bus. Similarly, there are some IO devices. Say there are some IO devices here. There is some output device, there is some input device. Okay, and there is one more important block called as DMA controller. So if you observe, this is how the communication is being done. Okay, right. Okay, fine. This is all the bus. This is processor, and there is one more important device called as DMA controller, direct memory access controller. Okay, and this is some output device, and this is input device. And the two pins which are present are hold and hold acknowledgement. This is hold and hold acknowledgement. Okay, fine. So let us discuss how actually the sequence will be performed here. And this is memory. Okay, fine. If you can follow through one processor, it's not a big deal to understand the other process. You can easily catch up. Fine. So here you know about the processor and the memory block, input output device. What is this block called as DMA controller? What is this DMA controller all about? DMA controller, DMA stands for direct memory access. There are some IC numbers for this. So it has got an IC number called as 8257, or advanced is 8237. So how it works, we shall see stepwise one by one. And say here, for example, the output device is here, the DVD port or DVD writer, let us say, or CD writer, whatever it is. Let us discuss how actually it happens. Fine. Okay, these are IC numbers. Okay. So what is the difference between a processor and controller? I am just coming to the very basics again. So you know that processor contains, let us say, processor contains, or the microprocessor contains ALU, CU and registers, okay, and memory is outside to the processor. Is it clear? Memory is outside to the processor. Fine. And this processor is common, we are discussing about it, you know what is the architecture and all. Memory is always outside. But sometimes what happens is, whenever you communicate with the input output devices or memory, there are some intermediate circuits like decoders, latch, buffer, so on etc. multiplexers, so on etc. So whenever the processor is added with some memory and with some interfacing logic circuits, okay, and also with certain other circuits called as timers, or counters. What is the purpose of this? To provide certain time delay or to count number of events. In real-time applications, there are many such usages. Therefore, if the microprocessor logic is added with the memory and interfacing circuits and timers, and you want to put up all these blocks into a single IC, if you want to put everything into a single IC, then this is what we call it as microcontroller. We call it as microcontroller. So it is not there in your syllabus, nothing to worry, but microcontrollers and microprocessors differ in some features, like processor contains only these three things, but everything is outside. But for a microcontroller, I am just denoting it as mu-c. For a microcontroller, everything is inbuilt. This entire thing is as one IC. Some examples of microcontroller: 8051, Intel 8051. Okay, so what you can understand here is that microprocessor contains only three parts, remaining all are outside, but microcontroller contains everything on single chip. Sometimes we can call it a system on chip, right? Fine. So here it has got built-in memory, it has got built-in interfacing circuits, like not all, you may have some decoder circuits, okay, or you can have some encoder inbuilt, or you can have some latch, you can have some buffer. So many such circuits can be possible, tri-state buffer, so on, etc. Okay, tri-state buffer, so on, etc. So all these things can be possible. So timers and counters are meant for generating some time delay. Simple example is your mobile has got some alarm feature, that is timer circuit. Similarly, you can count some events. You can count some events by interrupts. Let us say you are going to some some mall, or going to some cricket stadium, or a railway station, or airport. You will find some security check-in gates. When you enter into the gate, a beep sound is produced. So that is counting number of persons. So how many persons are entering to the gate? That is a counter circuit. So if everything is put into a single chip, that is called as microcontroller. So some microcontrollers may also have like ADC, D2A converters also, analog to digital, digital to analog converters even. Fine. So one most important feature difference between processor and controller is microprocessor is meant for general purpose applications. General purpose applications, whereas microcontroller is meant for specific purpose applications. Specific purpose applications. So this is one of the important difference in the features of processor and controller. One such type of controller is the one we are going to study now, that is called as DMA controller. So this DMA controller is especially meant for transferring huge amount of data between memory and the IO device at a faster rate with the help of this DMA controller. Are you able to follow? Right. So now let us discuss what are the sequence of events which take place while transferring the data. Fine. Okay. Now observe carefully. Let us say I want to transfer 1 byte from memory to output device. This is the example I am considering. I want to transfer 1 byte from memory to the output device. What is the general sequence which may take place? One important thing I want to again recollect or remember or remind you people is that processor does not do any job without the instruction. It will do everything with respect to some instruction. Fine. To bring the data which is present in the memory into the microprocessor, see, memory cannot directly transfer here. Okay. For example, say it is some DVD writer, CD writer, whatever it is. So first the data should be brought from memory to processor. Now to bring the data, what is the operation called as? Bringing data from memory to processor. What is that called as? Memory read. But can you have memory read without the instruction? No. It means to bring the data, first of all opcode must be fetched, it will be decoded, then memory read is possible. Now the data is with microprocessor. I have to send the data to the DMA controller. So what is this operation called as? Sending data to the output device. What is that called as? IO write. Sorry, I'm sorry, it's not DMA controller, it is output device. 1 minute, let me just erase. So I have to send the data to the output device. So here, just for understanding purpose, I'm writing like this. So this data, I want to transfer it to the output device. Output device. Okay. So what is this task called as? IO write. But to perform IO write, again, what is required? Opcode fetch, IO write. It means to transfer 1 byte from memory to the output device, how many operations at least are required? At least 4 operations are required. Operations means it involves memory read, write, whatever it is. Now, for example, let us say I want to transfer, so for 1 byte 4 operations are required. Let us say for 1 kilobyte, how many are required? Obviously, 4 into 1024. That many operations are required. That is how much? 4096. Okay, these many operations. So it involves lot of memory access. That is waste of time. And hence, the point to be noted is that whenever huge amount of data has to be transferred between memory and IO, by considering the microprocessor is not a best option or best choice, because processor cannot do anything without the instructions. Are you able to follow? Without the instructions, processor cannot do anything. Then what to do? To help the processor, there is one more IC or a device called as DMA controller, by which we can directly command or control the data between memory and the output device. So that is the mechanism involved in the DMA. Now we shall discuss how actually the sequence flows. Right. Number one, let us assume that the devices can communicate among themselves. How it actually happens, let us see now. Okay. First, say that the device wants to take the service of this DMA controller. Therefore, what happens is the device will request the DMA controller, number one. This signal is called a DRQ, DMA request to the DMA controller. So this DMA controller can support some 4 IO channels based on the IC number. So the priority will also be possible here. So the DMA controller will receive the request from the device, and the DMA controller also requests the microprocessor on a pin called as hold. Now observe carefully, is hold signal high active or low active? Looking at this, what is high active, low active? If it is like this, that is low active. If this bar is not there, that is, if this bar is not there, then this is called as what? Low active. It is not there, this is called as high active. If bar is there, low active. Okay, fine. Now, how it actually happens, let us see. Okay. First of all, it has sent the path or a bus communication medium. These all address bus, data bus, control bus are under the control of microprocessor. So if anyone wants to use the buses of the microprocessor, it must take the permission of microprocessor. So the DMA controller taking the permission of buses itself is called as the hold signal. Therefore, number 2, the hold signal is activated. So observe carefully, whenever the hold signal, this is the hold signal, whenever the hold signal is high, immediately processor understands that someone is requesting for the permission of the buses, and hence the processor will complete the current task. It will send one response called as HLDA. This response is called as hold acknowledgement. After this HLD is given, it indicates that the processor is telling, I have given you the whole control of the buses. I am no more going to use the buses. Now you are the master of the buses. It is giving the permission to the DMA controller. And hence, as the DMA controller got the permission of buses, it is also informing the device that I got the permission. And that signal is called as DACK, DMA acknowledgement. It's called as DMA acknowledgement. After this sequence, whatever the buses are present, all these buses are under the control of DMA controller. And hence, this DMA controller will supply the memory address, same as the program counter. There will be some register inside. So this will supply the address and the count will be loaded into this DMA controller. The data will be directly transferred. There is a path which forms here, and the data will be transferred from the device to the output device. So this is number 5. So unless until the whole data is transferred, the hold signal remains high. So if you observe here, the hold signal will remain high unless until the whole data is transferred. Now observe carefully. How does the processor know the data is completed? It means till the data is completed, processor cannot do anything. That state of the processor is called as idle state. Till this data is being transmitted, processor cannot do anything. That's called as idle state or wait state for the processor. Why? There are no buses. It cannot read, write, कुछ भी नहीं कर सकता है. So इसको बोलते हैं wait state या idle state करके बोल सकते हैं. It's called as wait or idle state for the microprocessor. Whenever this is happening, processor cannot do anything. Once this data is transmitted, the DMA controller will now inform the processor that data is transmitted. How does it inform? It will now pull down the hold signal which was high to the low. Once the hold signal comes low, then automatically DMA stops. Therefore, the processor understands that data transmission is completed, and this mechanism is called as direct memory access operation. So, till the whole data is transferred, the processor cannot do anything, the hold signal will remain high. So, what is general meaning of hold? Hold means pakad ke rakhna. Same thing. जब तक पूरा डेटा ट्रांसफर नहीं होता है, पूरा बस का कंट्रोल ए पकड़ के रखेगा. उस समय प्रोसेसर बिल्कुल कुछ भी काम नहीं कर सकता है. अगर इंटरनली कुछ होता हो सकता है, बस बाहर का काम रीड राइट कुछ भी नहीं कर सकता है, इंस्ट्रक्शन ही नहीं आएगा अंदर. दैट इज हाउ द ऑपरेशन विल बी डन. सो प्रोसेसर कैन नॉट डू एनी टास्क, इट विल जस्ट प्रेजेंट इन बी इन द आइडल स्टेट और वेट स्टेट. That is how the sequence will be present. Now you can write few points. What is the purpose of DMA? What is hold? What is the sequence which is involved here? You can write down few points. Purpose of DMA. Purpose of DMA. When huge data is to be transferred between memory and IO at a faster rate, direct memory access operation is used with the help of DMA controller. Now you can write hold. Write the explanation about the hold. High active input signal of the processor which receives the signal from DMA controller. Requesting the buses for DMA operation. When the processor receives hold signal which is high active, the processor completes the current operation and responds with HLDA, hold acknowledgement. The DMA controller sends an acknowledgement to the device which has requested the service. After this state, the control of buses is relinquished. Relinquished means the control is granted to. Control of buses is relinquished to DMA controller. After this state, the data from memory is transferred to output device or from input device to memory. Till the whole data is transmitted between memory and IO, the hold signal remains high. After the data transmission is completed, the hold signal is pulled down by DMA controller such that the control of buses is again taken over by the processor. This process is known as direct memory access operation. Direct memory access operation. The DMA controller can support 4 IO channels, 4 IO channels, with respect to priority. Okay. Now, my question is, through processor also there is some mediator, through DMA also there is some mediator. Then what is the use? What's the use of it? Here, DMA is meant for fast transfer of data. With respect to processor, what was the disadvantage? You are using the fetch number of times, memory access is more, time is wasted. But how is DMA advantage as compared to the processor? See, DMA controller is also something like one of the processor. So how it happens, let us see now. DMA controller also contains some registers inside it. Like for example, let us say this is DMA controller. It contains 2 important registers. One is called as address register. Other one is byte count register. Byte count register. For example, say that you want to transfer the data from some memory location. Let us say the location is 6000H. You want to transfer some 1K data, 1 kilobytes of data. Okay, right. Now observe carefully. Once the control is given to the DMA controller, now DMA controller address register will act as program counter that will place the starting address into this address register. For example, the data should be brought from 6000. How much data should be brought? Some 1 kilobyte. Means some count will be loaded here. 1 kilobyte means 1024 bytes in decimal. For example, in hexadecimal something different. Let us say, I am just writing as decimal. Don't worry about it. If you want to write hexadecimal, it is 400H. Right. Now, the address is supplied here. First byte is transferred. Immediately, the count will be decremented to 1. So, it will check the count. Immediately, address will be incremented by 1. See, is it 0 or not? It will check. If it is not 0, again, the address is placed, so on, etc. The bytes will be transferred. At the last, when the count becomes 0, then the condition is false. We have studied about the flags. So, when the condition is false, the data stops. So, that is why the DMA controller doesn't require any instruction. So, you can write the point like, by using DMA controller, the speed of operation is increased as it does not require instruction for every single byte. Once the count is loaded into the byte count register and the address of data to the address register, till the count becomes 0, the data will be transferred. So, the question of opcode fetches will be reduced. That is how actually speed can be, or speed of data transmission can be increased by using the DMA controller. So, that is about hold and hold acknowledgement. So, what is hold acknowledgement? It is very simple. Hold acknowledgement is output signal in response to hold request. That is about the DMA controller. So, you might have seen the status of this hold like these 3 signals. So, what is the status we have written in the previous topic or slides? For DMA, this was Z and cross cross. Why? For the hold signal, this was the status. Why? Because while DMA is being performed, this signal of processor is not required. It goes into high impedance state, and processor is not performing any task. The DMA is performing the task. That is why these two are also not having any value. That's the meaning of this. So, this is how we have completed the explanation of all the pins which are present in the 8085. But for the most of processors, this basic processor logic has been implemented and has been devised or designed in such a way that the speed can be improved, more memory can be handled. That's about the different types of signals which we encounter in a particular microprocessor. I hope you have understood all the 40 pins which are present in the microprocessor 8085. So the important things is we have to note down is that in the processor design, how much maximum memory can be connected. So this is important, and how do you connect the memory chip, the other notation, and while finding the starting address, ending address, I have given you some problems. Okay, and further we shall discuss how to connect the processor memory, so on, etc. Right. So very few formulas, but more analysis is required for the microprocessor discussion. Okay, hope you understood. We shall solve certain questions based on this data, whichever has been discussed till now. We have discussed what is the actual meaning of DMA operation and what's the purpose of DMA operation, how actually the speed can be improved with respect to the DMA operation. We shall also discuss what are several modes which are present in the DMA operation. So the main purpose of DMA is to transfer huge amount of data between memory and IO at a faster rate without the intervention of the microprocessor, because the processor uses instructions and it consumes lot of time to access the instruction, that is fetch the instruction from memory. Therefore, accessing the instruction now and then will increase the execution time, and hence to avoid the wastage of time we go with the DMA operation. Fine. We shall also discuss the modes which are involved in this particular DMA operation. So there are three modes of operation. One is called as burst mode, cycle stealing technique or short burst mode, and interleaved DMA. What is the meaning of burst mode of DMA? Burst mode of DMA means, for example, here let us say the IO device is only one which wants to share the buses of the microprocessor. So if you consider the hold signal will remain high unless until the whole data is transferred. So whichever the operation we have discussed in the normal DMA operation, so the hold signal first raises high, it should remain high until unless the whole data is transferred. So that is called as burst mode of transfer. It means that the total data is transferred at a time. But the point to understand here is that the microprocessor is completely held up during this period of transfer of the data. And hence, we say in the burst mode, for example, say CD writing or CD burning operation. We call the writing of data into CD or DVD is called as burning. Now, what happens is, for example, if you want to burn the data, generally what we do to burn the data? So, you will select the file, then it will ask the question, which files you want to burn, so on, etc. You will select the file. Then once you click on the burn operation, you cannot close that window, you cannot stop that operation unless until the whole data is transferred. It means in the burst mode of operation, the processor is completely hanged up because of the usage of buses by the memory and IO device. That is called as burst mode of operation. So this mode is the example, for this mode the example is like CD burning or DVD burning. But one thing is important here, during this period of time, the processor is held up. So processor cannot do any job. So that is why we say that the processor is present in wait state or idle state. It means interference is more for the microprocessor. Is it clear? That's what we say. Interference is more. So here interference means not getting disturbed. How long the processor is idle without any job? That is what we are calling it as interference. Okay. So here the wait state or processor is present. Processor is in wait state or idle state. So here we say interference is more. More interference for processor. So here interference means not getting disturbed, it is idle for long time, that is called as more interference. Example is CD burning or DVD. Come to the next one. What is cycle stealing technique or short burst mode? In the second technique, when the IO device is 1 here, that is the burst mode. Now 8257 IC can support 4 IO channels. Let us say the IO channels are more, means more number of devices want to access the data from memory. But bus is only one. So now it will be something like time sharing type of technique, time division multiplexing type of concept. So what happens is the processor will not, the data between the memory and IO device will not be continuously transferred by one IO only. The buses are shared with different IO devices. It means that it is something like time multiplex. So what happens, for example, let us say the total data to be transferred is something like 10 KB. Okay. So this 10 KB of the data is not transferred one stretch, it is transferred in short burst. Burst means the data. Therefore, first device, for example, device 1 will be transferring 1 KB of the data. Okay. So other chance is given to device 2, then that will transfer the data, some x KB of data. Okay. So like this, here some x KB of data. Next again some device 1 will be transferring the data, device 2, so on, etc. Like this, the total data is not transferred one stretch. But here what happens is, in the first case the processor was idle completely, but in the second case the processor is not idle completely. It may use the buses in between the transfer of the devices, means chance for each device is given at a particular instant of time. Therefore, the processor may use the buses sometimes in between. So that is what we call it a short burst mode or cycle stealing technique. Okay, so in the second example, we say that the number of devices or IO devices which use the memory through the DMA operation are more than 1. That is the cycle stealing technique. And the third case, now observe carefully. In the first case, interference is more. In the second case, interference is less or more? Less. What is the meaning of interference? How long the processor is present in the wait state or idle state for the buses. So here, interference is less. So interference is less. Okay. Interference is less. That is called as short burst. So in the cycle stealing technique, the data is stored in the transferred in the terms of blocks, and the blocks are transferred in a particular interval of time. So here the total data is divided into blocks, and these blocks may belong to different devices also, not same device. That is how actually the short burst technique can be involved. So you should understand that depending on the number of devices available, the internal circuitry of the computer will decide how to provide the time period for the buses. Fine. So that is automatically done. There are some settings, means control words are exchanged between the processor and devices. Those are called as some handshake signals. That's about the short burst mode or cycle stealing technique. The third one is interleaved DMA. In the first case, the processor time is completely blocked. Second case, some of the time it is active. But some or the other way, processor is busy sometime. So to avoid that, the third one is used. What is the meaning of interleaved DMA? So what happens here? Means I want the buses should be used by the devices, and at the same time processor should not also be in a quiet state or idle state. So what to do for compensation of such type of task? That is called as interleaved DMA. So what is interleaved DMA? In case of interleaved DMA, the buses of processor, see, this is called interleaved DMA. What happens here is, for example, say the processor is present here, okay, memory is here, assume some opcode in the memory, some instruction is there, okay, some instruction is there. So here the instruction will be brought into IR instruction register. This is the decoder. Okay, let us say first for any instruction opcode is fetched. Okay, so in the opcode fetch, first the instruction is brought into the instruction register. Opcode is brought here. Fine. Okay, PC is placed on the bus, opcode is brought and decoded. Now tell me, during this period of decoding, see, it is happening inside the processor. Now once opcode is fetched, I am just marking like this, once opcode is fetched, during the decoding process, Is there any purpose of the bus? Is there any requirement of this bus? Is there any purpose of the bus? No. Therefore, during this decoding time, the buses are used for DMA. But in this type interleaved DMA, it is very short duration of time for the decoding process, and hence what happens is in this mode only one byte is transferred per instruction. So in interleaved DMA, the buses of the processor are used for DMA operation only when the processor is doing some internal operation, something like decoding operation of instruction. Therefore, once decoding is done, again it may require the buses for read-write operations, so on, etc. So that is why in interleaved DMA, 1 byte per instruction. Why 1 byte per instruction? For example, say every instruction 1, for example, say instruction 1, opcode fetch in decoding. In this time only 1 byte is transferred. Okay, 1 byte transferred. Again, after decoding, again buses may be utilized for read-write operations. So 1 byte is done. Again, instruction 2, again opcode fetch for second instruction, again decode, and 1 more byte is transferred. So like this, byte by byte is transferred per instruction. That is why it is called as interleaved DMA. And hence, this is how we can say different modes of DMA can be visualized based on the time which is available with the processor. So these all are decided by some control words before. That is how actually the operation can be done. Means between the processor, between the DMA controller and the device, there will be some sort of signaling. So those signals are generally called as handshake signals, how the device communicate among themselves. Okay. So these signals are sometimes called as handshake signals. Handshake signals means control signals. Handshake signals means the control signals which are present. Control signals. So these handshake signals are something like the signals exchanged between the devices. Signals exchanged between the processor and IO devices. Processor and IO devices. So based on the handshake signals, they will be communicating between each other. So this is how we can discuss or consider the DMA operation. I hope you have understood how actually the sequence of events will take place with respect to the DMA. You may get a question based on the modes of operation, or you may get a question based on the sequence of events which take place, so on, etc. So hold acknowledgement, I think already we have discussed this signal. Hold acknowledgement, simply it is one output signal in response to hold request. That's all. That's about the modes of DMA. Whatever the architecture topic we have discussed till now, let us solve certain questions. Well, we have already solved some questions, but more number of questions will give you more practice. So for GATE, you have to practice lot of questions which are required for the concepts. So more you practice, more confident you will be in the exam. Fine. So let us solve the questions one by one. So try to understand. So this question is about the basic data of number systems and also a couple of problems on memory and also on the architecture registers which are present. Fine. Look at the question. Using a 4-bit 2's complement arithmetic, which of the following addition will result in an overflow? Fine. You know some flags, overflow. What is overflow? Overflow is meant with respect to signed operation, signed data. So here he says 2's complement arithmetic, means they are using signed number system, right? Always overflow. What is overflow flag? Overflow flag, I told you some conditions. Overflow, I am denoting it as V, may take place in 2 conditions. How? Number 1, the data is 4 bits only. Observe carefully. 4 bits means in signed data, what is the notation? 4-bit signed data. 4-bit signed data. So how many bits are there? D3, D2, D1 and D0. Okay. D3, D2, D1 and D0. Here MSB is a sign bit. Don't worry about this. It is sign bit. 0 is positive, 1 is negative. And these 3 bits will give you the magnitude. they provide the magnitude. Therefore, how do you consider overflow? Overflow means the magnitude should not override the sign bit. If it is overwriting, it means here, what are the conditions? From D2 to D3, if you have got some carry, then overflow will take place, and at the same time, D3 to carry should not be present. Then only we say that overflow is 1. That is first condition. Or you can also say that D2 to D3, D2 to D3 bit, there is no overflow, but overflow is there from D3 to carry. Then also we say overflow is 1. If both of them occur, it means like if D2 to D3 also it is present and D3 to carry is also present, then we say that overflow is 0. In short, we can say that overflow will occur when we perform some addition operation or some addition operation here if the numbers have got same sign. Okay, that is one condition. So now check very easily, you can answer now. Tell me, look at this data. Look at this data. Sign is same. Will overflow occur? No. Here, sign is not same. The second one. So now how to answer easily, logically, think carefully. First one is wrong. So in the options, wherever one is there, remove it. In the answer, wherever one is there, you just remove it. So A भी नहीं होगा, 1 है ना यहाँ पर, 1 है, so A भी नहीं होगा answer, and 1 यहाँ पर, A भी नहीं होगा. So what is the only chance? That is 2 and 3. Just check 2 and 3, you'll get the answer. So very simple. Tell me, 0, these are also same, but observe carefully what happens for the data. Now tell me here, now add this data. What is the data here? What's the data? 0, 1, 1, 0, 7. Okay, that is 7. Okay, now let us solve this data. Very simple. So here I am writing like this. So 0, 0, 1, 1 plus 0, 1, 1, 1. Now observe carefully, forget about this bit. It is D3, this is D0. Okay. Now, okay, this is D3 bit and this is D0 bit. Okay. Now add the result, 1 plus 1, 0, 1. The 1 plus 1 plus 1, 3, 1, 1, 0, 1. While adding two positive values, can you get a negative result? No. That is why we say that overflow has occurred. It means in this options, what is the correct one? B is the correct one. B will be the correct option. Is it clear? So B option will be the correct option. Very simple. So what is the logic I have discussed here? If first one is wrong, remove the options wherever one is there. That is a shortcut. So you'll save some time. That's it. That is first one. Hope you have understood. Right. So there are a couple of questions as such. Always understand when the question says 4-bit 2's complement arithmetic, definitely you should understand that that is a signed type of operation. Overflow will be considered with respect to signed numbers. Fine. Go for the next one. Go for the next one. This is number 2. See, this is problem number 2. Okay. See, while discussing the topic also, I may give some questions, and these are some problems after some certain topic which is present. Okay, let us not consider this. Okay, some data is required for solving this question. Okay, this is question number 2. Right. Read the question. A processor has carry, overflow and sign flag bits as part of its program status word. You already know what is the meaning of PSW, status register. Okay, performs addition of the following 2's complement numbers, 0, 1, that is 4D and this is E9. Fine. After the execution of this addition operation, the status of carry, overflow, sign flag respectively. Remember carefully. Whenever the question speaks about this overflow, whenever it talks about overflow, then you must add in binary fashion, because to find out the overflow, always remember the data bit, the carry from dn minus 2 to dn minus 1 should also be there. Carry from bits dn minus 1 to carry should also be there if overflow is 0. If it doesn't happen, overflow is 1. So you should always keep it in your mind that when the question talks about overflow, solve the question in the binary, individual bits only. If overflow is not given, only carry or sign is asked, simply directly convert into hexadecimal, perform it, you'll get the answer. Okay, let me solve the question how it can be done. So very simple. So here the data is, what's the data? There is 8-bit data. So look at the data, how it can be written. It is 8-bit data. Okay, so the data is 4D, that is 0 1 0 0. It is 1 1 0 1, and the other one is E9 plus 1 1 1 0 1 0 0 1. This is the data, and never forget that the MSB bit is always for the sign bit. Okay, this is D7 bit, this is D6 bit, so on etc. D0 bit. Now try to find the addition of this. So what's the value obtained? 1 plus 1 0, 1 carry, this is 1, this is 1, 1 plus 1 0, 1, 1, this is 1, 1 plus 1 0, carry from D6 to D1. Therefore, this is again, this is 1, this is a carry 1, 1 plus 1 0, 1, and hence the carry is 1. You got a carry from D7 to out of MSB. Okay, so what is the rule for overflow? Either you should have a carry from D6 to D7 only, or D7 to carry flag. Both have occurred. So what is overflow? 0. Because if you are adding this data, if you take this 2's complement data, it is a negative value, this one is a positive value. But now you have to check what is the magnitude of it. If you do that, you will get the actual answer. Okay, so what is the condition here? Very simple. There was a carry from D6 to D7. Okay, there was a carry from D6 to D7 and also D7 to carry out of D7 MSB. So therefore, overflow will be 0. To make it simple, whenever you get like this, the simple operation is use XOR operation for the values. Use XOR operation for carry from D6 to D7, carry from D7 to outside, out of it. Therefore, you can take these carries. For example, I am taking this one. How much you got? Carry flag, and other one is D6 to D7. So carry from D6 to D7. I am pointing out like this. Okay, right. So you take these two. Very simple. What is the XOR gate truth table? 0 0 is also 0. 0 1 is 1. 1 0 is 1, and 1 1 1 1 is 0. So you should consider these two things. So in these two cases, overflow will be 0. In these two cases, overflow will be 1. That's it. So whenever you get a question, you just think of like this, you easily understand what is the value. Hope you have understood. Okay, right. So what is the option here? Option is B. Option here is B. B is the option. 1 0 0. Fine. So carry, be careful while writing. Carry flag was 1, overflow is 0, and sign bit. What is sign bit? This is sign bit. This one is called as sign bit. Sign bit is always MSB bit. This is sign bit. The sign bit is 0. So it is showing the result as positive. Okay, if it is not visible. So the sign bit here is 1. This is sign bit. Sign bit is always MSB bit. Sign bit is 1. So this is 1 0 0. That's how we can solve the question. Fine. Okay. These are analysis type of questions. You must be very cautious while solving these questions. Okay, read the question carefully. Okay, read the question carefully. The following are some events that occur after a device controller issues an interrupt while process L is under execution. Okay, right. So here some process L is taking place, okay, and in the meanwhile some interrupt has occurred. Now do you remember what are the sequence of steps the processor takes or the controller takes while responding the interrupt? Number 1, the next address, whatever was the PC will be having the next address of instruction. Okay. The program counter will have the next address of instruction. So this next address should be first pushed on to the stack. That is number 1. So when interrupt occurs, the first thing is whatever the process was continuing, the status of process may be pushed on to the stack memory sometimes. So in that, PC is also included. In some process, we say the next step is PC is pushed onto stack. In other cases, we say PC is pushed onto stack and the register status like program status word is also pushed onto stack in some kind of process. Overallly, we can think that the status is pushed onto the stack. So look at this. He's asking what is the sequence of events. I will explain the data. You try to answer the question. Okay. So first, the status is pushed onto the stack, means this value PC or the status is pushed onto stack. Then the program control will go to the program or interrupt service routine. After completing the interrupt service routine, generally the last instruction is written. So after this, the program will come back to the main program which it was doing. This is number 3. Okay, sorry. This is number 3 and this is number 4 and this is number 5. It means it will come back to the main sequence by taking out the data which was stored by it, like PC data will be stored into stack. It will pick up the data, pop the stack and come back to the main sequence. So this is how the sequence of events can be continued. So therefore, you check which option is correct option. You can check yourself. Number 1, when the process running, interrupt occurred. So what is the sequence of interrupt? Now process is running, I have taken as 1. You count from interrupt occurred. So interrupt occurred. So what is the first thing interrupt occurred means? 2. What is 2? Program counter value or the status of L is pushed on to stack. So look at this where it is. First one is the processor pushes the process status of L onto the control stack. Next one, the processor finishes the execution of the current instruction. Yes, that is true. This instruction, whatever the instruction which was occurring here, some instruction is there. There is some instruction being executed. At that time, interrupt occurred. So it will first finish the instruction. That is number Q. That is the first one. So if I mark the sequence, it will be easily understood for you. So number 1. Number 1 is Q. The processor finishes whichever the instruction it is doing. Then interrupt has occurred. So it will complete this first. Then it will push the status. So the processor pushes the process status L, that is number 2. That is number 2. Next, after pushing the status, it will go to the interrupt service routine. Look where it is. The processor executes the interrupt service routine. That is correct. The processor loads the new PC value based on the interrupt. That is correct, no? Before going to the ISR, first it has stored the PC value. Then it will load the new value of the process. That is number 3. It will load the address of new program. To run the ISR, PC will be updated. So the current value here, I am just showing here, the PC will be loaded with the ISR value. That is number 3. Then number 4 is it will continue the ISR. This is number 1. This is number 4. It will run the interrupt service routine. And number 5 is the processor, after completing it, with respect to the written instruction, whatever the data was stored into the stack memory, it will again bring the data back, means PC value back and load the PC value. So that is number 5. Number 5. So that is how the sequence will go on. So look at what is the correct sequence in the options. What is the correct sequence? First one is Q, next is P, next is T, R and S. So they are very, very important questions. Same concept will be again discussed in the instruction called as call. Same thing happens for the call instruction also. Okay. call instruction also. This is a sequence, very important sequence of control transfer. Whether it can be call or interrupt, the sequence of steps are same. So, what is the correct option? The correct option is the A. A is the correct option. Okay, it is not visible, I am writing with this. A is the correct option. Okay, right. Next, this is one interfacing question. The chip selects, okay, you can just take the numbers, I am not writing the numbers of questions, you just write the numbers. The chip selects logic for a certain DRAM chip in memory system design is shown below. Assume that memory has 16 address lines denoted by A15 to A0. What is the range of address, means memory map is asking in hexadecimal of the memory system that can get enabled by the chip select signal. He is asking for this chip select signal, what is the memory map? Some memory is connected here, some memory will be connected. He is asking what should be the range of that particular memory chip. Okay, fine. So, let us solve the question. Very interesting, very easy also. Here there is some memory chip, okay, and this memory chip capacity can also tell me. Here 16 address lines are there, among which how many are used? 5 lines are used. 16 minus 5, how many lines are there for the memory chip? 11 lines. So, tell me 2 power 11, what should be the capacity? 2 KB is the capacity of memory chip. Very simple, 16 minus 5 is 11, 2 KB. So, this memory chip is some DRAM chip. So, this is DRAM memory chip. So, what's the value you got with this respect to DRAM? So, it is a 2 KB DRAM chip. So, 2 KB DRAM chip should have how many address lines? 11 lines, A0 to A10, and it will also have, by the way, it is a read write memory. So, D0 to D7. So, it will also have a read signal, it will also have a write signal, read signal and write signal, and the chip select is connected through this decoding logic. So, this is the decoding logic given to you for the chip select. So, this is chip select given. But here observe carefully, is it low active or high active? High active. So, we have to keep that in the mind. It is not low active, it is high active, means chip select does not have a bar, it is. So, the whole thing will be high active or low active, both are same. Now, very simple, tell me what is the decoding logic you got here. So, A15, I am just writing here, this is A15, A14, that is 13 and 12 are bubbled, bubble means negated, this is also bubbled, and the last one is directly bubbled. Very simple. So, tell me what are the values? This is 15, this is 14, A14, A13, A12 and A11. So, now tell me what is the value? Okay, this is A12 and this is A11. So, very easy. What is the output of this gate required? Which gate is this? AND gate. So, AND gate, you have to see that all the input lines are high, 1, 1, 1, 1, 1. You have to see that all input lines are high. So, what should be the value? Then only the output will be 1, then only the chip select will be done. So, very simple. Tell me what's the value? I am just interpreting here. You tell me. These are directly connected. So, what must be the value? What must be the value? That is 1. This is also 1. This is bubble here. So, NOT gate is there in between. To get 1 at the output of NOT gate, the input should be 0. This is 1 actually, okay. So, this is also 0 and this should be 1. That's all. That is the decoding logic. How to find starting address, ending address? Very simple. Put all zeros and put all ones. How do you solve this? Very easy. It was how much? 11001. So, just put the values and you'll get the answer. So, how to solve this? Very easy. That is A15, A14, A13, A12, A11. From A10 to A0, this is simply range. A0, this is range. Okay. Right. So what's the value? How much you get? Let us see now. Okay. Now write the decoding logic. What is decoding logic? It is simply, what's the decoding logic? How much you got? 11001. So first you have to find out the decoding logic. That is simply 11001. Okay, 16 lines. Now starting address and ending address, very easy. Remaining 11 lines, put all zeros. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. That's all. That is starting address. You have to give the address in the hexadecimal form. Just write 4 bits as 1 nibble, 1 nibble, 1 nibble, 1 nibble. Tell me, what is this address? How much is this? If you write this equivalent hexadecimal value, how much you get? This is 0, 0, 8. This is C. So this starting address is C800H. If you want to find the ending address, now tell me, can you change this decoding logic? No. To select the chip, this pattern should be same, it should not change. Therefore, copy this value, simply copy the value, that is 11001. Decoding logic is same. Now put all ones. 2, 3, 4, 1, 2, 3, 4. Now find out what is the equivalent hexadecimal value. What's the value obtained? C, F, F, F. So this value is simply C, F, F, H. So this is what we call it as memory map of the given interfacing logic. Very simple. So tell me, what is option? Can you look at this option? What's option? So did you understand? So that is how we have to solve the question. Tell me what's option? C8002 CFF. So the option B is the correct one. Next one. If there are m input lines and n output lines for a decoder that is used to uniquely address a byte addressable 1 KB RAM, then the minimum value of m plus n is. Fine. First of all, to solve this, you should know what is the meaning of decoder. Decoder will have m input lines and 2 power n output lines. So this is some decoder. Okay. Say this is some decoder. This is some decoder. Okay. So this decoder has got m input lines and 2 power m is equal to, that is n output lines. Decoder will have m input lines and 2 power n output lines. That is why we say this is 2 power m by some n, whatever it is, and decoder. This is a decoder. Okay, these are the output lines, y02, yn minus 1, and these are some input lines, whatever it is, c, b, a, so on, etc. So input lines I am just writing as x0 to xn minus 1, this value. Okay, don't get confused, this n and this n are different, don't get confused. Fine. Now he is saying this decoder should be able to interface one memory. Okay, so tell me, what memory is this? 1 KB RAM. It is just simple, understand the question properly. 1 KB RAM, 1 KB RAM. So tell me, 1 kilobyte, it is byte addressable. So per location, 8 bits are there. 8 bits are there. How many locations are there in the memory? 1 KB means how many locations? 1 KB is equals to 1024 bytes. Forget about the bytes. How many locations? 1024. How will you get that 1K? 1K means how much? 2 power 10. Okay. It means to have 1024 registers, you have to decode 1024 registers. Means the first register is 0, the last register number is 1023. So these many addresses are required at the for the registers. So this n will become 1024. Very simple. If n is 1024, what should be the value of m? How many? 10. So this m is equals to 10 and n is equals to 1024. He is asking what is the value, the minimum value of m plus n is. Very simple, just add both of them. What is there? So add m plus m. M plus n is equals to 10 plus 1024, that becomes 1034. Okay, that becomes 1034. 1034. So this is how we can solve the question. I hope you have understood how to solve the question. That's why I told you, if you know the basic concepts. See, actually the syllabus for computer organization, which has been introduced newly, it matches with the computer science syllabus, some part. So that is why I am just trying to discuss the latest questions which were discussed in the CO, because as 2021 is the first paper for electronics people, I am just trying to make you people to cope up with the same type of questions. That's why I am taking the questions from some of the questions from computer science, and I will be mixing up both of them. Nothing to worry about it. Fine. So answer is 1034. So what is the? It's a fill in the blank given. Right. Next one, theory question. A device employing INTR line for device interrupt puts the call instruction on the data bus while. Now tell me, I told you that whether it is interrupt or call, it is same. These instructions like INTR, tell me why, how is INTR used? Can it be used alone? No. INTR should be used. Okay. INTR should be used along with RSTN, where n value is from 0 to 7. I have very clearly discussed the method of analysis of this INTR. Now tell me, the device employing INTR line for device interrupt puts the call instructions. So these instructions like RSTN are also called as 1 byte call instructions. Okay. So we have discussed in the theory part, like in the INTR discussion, the opcode is generated from outside. So when it is generated from outside, option A, when INT is active, hold is active, ready is active, none of this. Very simple. Hold is for DMA, ready is for slow peripheral. So what is the only thing left? INT. So the correct answer is this INTA. So INTA will be the correct answer, interrupt acknowledgement. Very simple. If you know the basic, you can solve the questions. Next question. A CPU generally handles an interrupt by executing an interrupt service routine. When does the CPU handles the interrupt? Very simple. Always understand whether interrupt or call instruction. Just think about this flow. You get the answer. Tell me. Whenever it gets interrupted, what happens? First one. It goes to interrupt. When does it go to interrupt service routine? Will it go to ISR? See, this is the interrupt service routine. Will it go to interrupt service routine? No. First, it will copy the value of next instruction PC into the stack. Then it will go to ISR, complete it. Then it comes back. Okay. Now observe first one. As soon as interrupt is raised, that is wrong. As soon as interrupt is raised, it will not go. This is wrong. Second one, by checking the interrupt register at the end of fetch cycle. Look at the next one. Let us see. By checking the interrupt register after finishing the execution of the current instruction. By checking the interrupt register at fixed time intervals. So don't worry about this. What is interrupt register? Whenever some interrupt occurs, there is mechanism inside the processor to store the status of these interrupts, vectored interrupts I told you, or whatever the interrupt it is. But understand, when interrupt occurs, processor will complete the last instruction, and I discussed in the case of INTR, interrupt request pin of the processor. Processor will always check the status of interrupt only in the last clock period of the instruction. So in the fetch cycle means, so what are the basic steps of execution? Basic steps of execution are, which steps? What are the basic steps? Basic steps are fetch, decode and execute. 1, 2, 3. So only in the last lock means in the execution time only it will check for the interrupts, whether the interrupt is present or not, it will check only in the last lock. So according to this concept, definitely the second should also be wrong, but in the second case he is saying it is completing, it is checking the interrupt in this one. No, it doesn't happen here, it checks only in the execution time. So last one, third one, by checking the interrupt register after finishing the execution of current instruction, by checking the interrupt register at fixed time intervals. This is not the case. So after execution of current instruction means at the last lock only it will check. So the correct one should be this D. So this is also wrong. That is how we can understand. So therefore, this concept of interrupts you should understand very, very clearly. Fine.